So now I want to figure out what the pH is once I've added 49 milliliters of 0.1 molar sodium hydroxide to my analyte. So it's a similar calculation to what we did before. The 49 milliliters multiplied by that 0.1 molar concentration tells me that I've added 0.0049 moles of hydroxide total. If I subtract that from the number of moles of protons that I had originally, that tells me that I'm left with only 0.0001 moles of protons in the solution now. So you can start to see a pattern here. Now, adding that to my table, I can see that I've really drastically reduced the number of moles of protons in my solution. So now, if I take the number of moles of protons over the total liters of the solution, and then take the negative log of that, that gives me a pH of 3, much larger than before. So what's happening is I'm getting close to extinguishing all the protons in my analyte, and I'm really getting close to the equivalence point, and the pH is starting to shoot up. If I get even closer to the equivalence point, adding 49.9 milliliters of sodium hydroxide, that's going to look like a similar calculation, except even more extreme. This has added just a little bit more, 0.00499 moles of hydroxide, and that's going to leave only 0.00001, okay, 4 O's, moles of protons in the solution. So that means I'm getting a really low concentration of strong acid. Taking this over the total volume and taking the negative log, I get a pH value of 4. So the concentration of hydronium has gone down by an order of magnitude, or 1 log unit. So I'm really getting close to the equivalence point, and now you can imagine what's going to happen once I've added 50 milliliters of 0.1 molar NaOH. At that point in the titration, that 50 milliliters of 0.1 molar NaOH results in 0.005 moles of OH minus that I've added total. This is exactly equivalent to the amount of protons that I started out with, and it completely wipes them out. It completely wipes out the 0.005 moles of protons that I started out with. This is the magic point in the titration. This is what we call the equivalence point. And at the equivalence point, we have no moles of protons in solution, nor do we have any moles of hydroxide. They are perfectly balanced. We've added just enough hydroxide to wipe out all the protons and make water. Thus, there's no calculation to be done. It's neutral. The pH is 7. This is going to be true for any strong acid, strong base titration. At the equivalence point, the pH is going to be equal to 7. We have no calculation to do. So I'm going to label this equivalence point, and this is also the point of neutralization, where I have effectively pure water with spectator ions floating around in it, and the pH should be 7. Now we want to calculate what the pH is once we overshoot the equivalence point. Here we've added excess sodium hydroxide. So hydroxide is going to start controlling the acid-base chemistry of the solution, and we should see the pH go up above 7. So once we've added 51 milliliters of sodium hydroxide, that multiplied by the 0.1 molar concentration tells me that in total I've added 0.0051 moles of hydroxide. Now remember, 0.005 of those moles were neutralized by the hydrochloric acid. So out of those 0.0051 moles of hydroxide, 0.005 moles of them were taken out by HCl, and that leaves an excess of 0.0001 moles of hydroxide. And that is going to determine the pH of the solution. So we can figure out the pH by calculating the molar concentration of hydroxide, 0.0001 moles of hydroxide, over the total volume of the solution. At this point, it's 51 plus 50, so 101 milliliters, which I convert into liters for the denominator here. That gives me a molar concentration of 0.00099. Now, I can take the negative log of that to get the POH, which is 3. And subtracting that from 14, I get the pH, which is 11. So, as predicted, the pH goes up quite a bit once hydroxide starts controlling the pH of the solution. I don't have any moles of protons that I need to worry about here because I'm really just using hydroxide to figure out what the pH is at every point. I can do exactly analogous calculations for 60 milliliters and 80 milliliters of sodium hydroxide, resulting in 110 milliliters total and 130 milliliters total, respectively. It's going to be similar to what we just did in the sense that I'm going to have excess hydroxide, in this case 0.001 moles of excess, calculate the molar concentration of hydroxide, get the pOH, and then the pH. So doing those calculations for both 60 milliliters and 80 milliliters, you can see that the pH is 12, and then it goes to 12.4. So the pH is not changing as drastically. It's starting to really level out at the end of this titration here once we've gone way past the equivalence point. So the reason I want to do that is because I want to plot a pH curve. So 12 and 12.4 will round out our data set here. In the next video, I'll show you how to take these data and plot them to make a pH curve for this titration.